The longest-running space mission is a testament to NASA's engineering, but recently, it discovered something that even the engineers can't explain. Voyager is the longest-running mission in the history of space exploration. About 45 years later, NASA is still in contact with both probes, which takes routine commands and transmit collected data back to Earth's deep space network. In this video, we'll talk about the most amazing findings made during the nearly 45-year Voyager mission. Make sure you stay tuned to the end of the video to know about everything the Voyagers found at the edge of the interstellar space. Before we begin, welcome to Discover Space. If you want to be a part of our space journey, don't forget to click the subscribe button and hit the notification bell next to it to be the first to know whenever we upload a new video. In 1977, NASA's Jet Propulsion Laboratory launched two Titan Center rockets, each carrying nearly identical space probes. These identical probes, known as Voyager 1 and Voyager 2, were built with the goal of studying Jupiter, Saturn, and their larger moons for a period of 5 years. After successfully completing all of its initial goals within 4 years, the Voyagers went on to observe the two outer giants, Neptune and Uranus. After that, they went on to more ambitious Voyager interstellar missions, which aimed to explore the furthest reaches of the sun's sphere of influence and beyond. Voyager 1 and 2 have already separated from the heliosphere and entered interstellar space after departing Earth at distances of 22 billion and 18 billion kilometers respectively. However, even the long-lived Voyager probes are running out of time. The probes will likely run out of power by 2025 and go permanently dark. In order to extend the mission for a few more years, NASA starts switching off the instruments on the probes. However, the probes will leave behind an incredible amount of data when they eventually go dark. Voyagers 1 and 2 were intended to have a 5-year mission, but the team of scientists and engineers made a variety of design decisions that allowed the probes to endure for a far longer journey. A long-lasting radioisotope thermoelectric generator found on each probe transforms heat from the decaying plutonium-238 isotope into electrical energy. The probes also contain 16 Hyzodine thrusters, including 8 backups and redundancy for the majority of its 11 scientific instruments in case of equipment failure. Most significantly, the launch took place at the ideal time. NASA took advantage of a once every 176-year alignment of the planets when the Voyager planetary mission was launched in 1977. This alignment not only allowed for flybys of Neptune and Uranus with little course correction, but also gave the probes a gravity assist from each of the giants they visited, achieving their effective velocity beyond what they could achieve with their own rocket propulsion. At the time, this concept had only recently been tested on NASA's Pioneer missions to Jupiter and Saturn. Voyager 1 left the ecliptic, the plane of the Earth's orbit around the Sun, in 1981, moving 35 degrees to the north. Later, Voyager 2 headed 48 degrees to the south and passed through the ecliptic. The cameras on both probes were turned off to save power after the Voyager planetary mission was extended to become the Voyager interstellar mission. The last image captured by Voyager 1 is the well-known shot of Earth as a pale blue dot, which is the furthest picture of Earth ever taken at a distance of almost 6 billion kilometers. However, the voyages of the Voyagers had just begun. The probes would have had to pass through the termination shock, where the interstellar wind encounters tremendous resistance from hypersonic solar winds, in order to enter interstellar space. After passing through the termination shock, the Voyagers would have to pass through the helioheath, where slowing solar winds accumulate and become hotter and denser, and then the heliopause, which marks the complete separation of the heliosphere from interstellar. Contrary to popular belief, our solar system does not stop at the beginning of the interstellar medium. Voyager 1 won't leave our solar system for good for another 300 years after it enters the Oort cloud, a massive region filled with billions of ice palestros that encircle it like a bubble. It will take another 30,000 years for Voyager 1 to leave the cloud and leave our solar system forever. The Voyagers make a remarkable discovery when they pass through the helioheath. The heliospheric current sheet is a ripple that forms as the sun's magnetic field spins in opposite directions at its north and south poles, similar to the rings that form when a stone is dropped into the water. This sheet, however, compresses as it encounters the termination shock, as if the edge of the pool were being hit by the ripples. These stacking ripples combined to generate magnetic bubbles follows the termination shock, as it was revealed by the Voyager probes. This indicates that the Helios heat boundary is not as smooth and distinct as previously believed. It is a shifting, magnetically bubbling environment instead. The Helios heat model has undergone a major change as a result of this untidy discovery. The Voyager 1 spacecraft entered interstellar space on July 25, 2012, making history as the first artificial object to do so. It was moving at an astonishing rate of 540 million kilometers per year, or 3.6 astronomical units. It was a revelation that Voyager 1 passed the heliopause at a distance of around 120 astronomical units from the Sun, because it was unclear exactly where the heliopause occurred. Funny enough, different early models placed it far further away from us or closer to Jupiter. Keep in mind that the heliopause is the point where the solar wind from the Sun is stopped by its collision with the interstellar medium, similar to the collision of two large bodies of water. Solar wind is the continuous outflow of charged particles from the Sun's outer layer, including electrons, protons, and alpha particles. In contrast, the interstellar medium is made up of charged particles, gases, and cosmic dust that was left over from the Big Bang and past supernovas. The heliopause border is an area equilibrium created when these charged streams collide and shift course. NASA initially questioned whether Voyager 1 had actually traveled beyond the heliopause and into interstellar space. The probe's plasma wave detector discovered an enormous rise in plasma density, 80 times greater than what it had seen in the outer helioheath, as well as an increase in galactic cosmic rays, as expected by models. But a curious event that should have happened didn't, and it surprised experts. Voyager 1 didn't notice any changes to the surrounding magnetic field after passing through the heliopause. In an area where the magnetic field of outer space are dominant, theoretical models predicted that the ambient magnetic orientation would change. Amazingly, however, Voyager 1 saw no obvious change in the surrounding magnetic field. Due to their confusion, NASA took over a year to confirm that Voyager 1 had indeed entered interstellar space. Voyager 2 followed Voyager 1 as the second artificial object to enter interstellar space on November 5, 2018, but at a slightly slower speed of 490 million kilometers, or 3.3 astronomical units per year. Similar to Voyager 1 6 years earlier, the crossing took place 120 astronomical units from the Sun, yet neither probe noticed any changes to the Earth's magnetic field. But something else caught scientists off guard. The Sun goes through 11-year solar cycles, during which its activity increases and decreases. When Voyager 2 crossed, solar winds were at their strongest. Models suggest that the heliosphere's size would vary with the solar cycle, therefore, Voyager 2 should have crossed it when it was expanding. The models were incorrect because Voyager 2 traveled the exact same distance to pass the heliopause as Voyager 1 had done 6 years earlier. This proved the importance of using field data to test theoretical models, such as the magnetometer result. We now believe that compared to what earlier models suggested, the boundary between the heliosphere and interstellar medium is far more twisted and chaotic. One popular theory holds that our Sun originated from a hot, highly ionized zone after the explosion of one or more supernovas, and that magnetic turbulence still exists today close to the heliopause. If so, the probe's instruments will likely be dark by the time they reach different magnetic orientation, due to their increased distance. The twin probe's cosmic travels have only begun, despite the historic Voyager mission likely coming to an end, but we must bid farewell to these cherished companions and move on with our own lives on Earth. And the Voyager mission is just the start of our exploration of space. That's all for this video. Thanks for watching. If you enjoyed, don't forget to like the video, also subscribe to the channel and hit the bell icon to never miss a new video. Also, let us know what you think about this image in the comments section below. Until next time.